Hello, my name is Oliver Harlan and I'm a reader in the School of Mathematics at the University of Leeds. In my research I use mathematics to study how liquids flow. For example, one of my projects looks at how drops form in an inkjet printer. To do this I need to be able to describe the position of the ink surface and the fluid velocity of the ink as it changes in time in 3 dimensions. Since position and velocity are vector quantities, we use vectors to describe these. And today I'm going to show you how vectors can be used to define straight lines in 2 and 3 dimensions. Although you probably already know how to write down the equation of a line in 2 dimensions, the vector definition is more natural and works in both 2 and 3 dimensions. Let us begin by considering how we would draw a straight line on a 2-dimensional plane, such as a piece of paper. We choose a starting point somewhere along the line and then use a ruler to define the direction in which we'll move our pen. As we move the pen along the line, we trace out a line of points that forms our straight line. Now let us use vectors to describe this process mathematically. We begin by choosing a point on the line, which we can call A. The position of this point is described by its position vector. In this example, it is -2, 2. Next, we define a direction along this line using a ruler. We can describe the orientation of the ruler using a vector parallel to it. In this case, we can use the vector B, which is at 2, -1. Now the position vector of any other point, P, say, along this line, can be formed from the vector sum of the position vector 0 to A and the vector from A to P. Since AP is parallel to B, it must be a scalar multiple lambda of B, so that we can write the position vector OP in the form of OA plus AP. This is called a parametric equation, since it involves a parameter lambda whose value can vary from minus to plus infinity. Each value of lambda gives a particular point along the line. For example, if we take lambda equal to 0, we get the starting point A. Lambda equals 1 gives us -2 plus 2, which is 0, and then 2 minus 1, which is 1, giving us the position 0, 1. Lambda equals 2 gives us the point 2, 0, and lambda equals 3 gives us the point 4, -1, etc. Our vector equation is in fact 2 separate equations for x and y coordinates of the point P. If we write OP as xy, then we have x is -2 plus 2 lambda and y is 2 minus lambda. We could eliminate lambda between these 2 equations. From the x equation, we have 2 lambda is x plus 2, and substituting into the y equation gives us y equals 2 minus x over 2 plus 1, which is equal to 1 minus x over 2, which is the more familiar equation for this straight line. The great advantage of using the vector equation is that we can use exactly the same form in 3 dimensions. Let us find the equation of the line through the points A and B. We can choose either point as the starting point, so let us take the point A, which in this example has position vector 2, -1, -5. Now for a vector parallel to the line, we can use the vector between A and point B, where B now has position vector 3, -4, -3. This gives us the vector AB, which is the difference between these 2 position vectors, and is given by 1, -3, 2. Therefore, the position vector R of a general point P on the line is given by the sum of the position vector of A plus lambda times the vector AB. Or alternatively, we can think of it as the position vector A plus lambda times the difference between the position vectors of B and point A, giving us 2 -1 -5 plus lambda times 1 -3, 2. Lambda equal 0 gives us the point A, and lambda equals 1 gives us the point B. We can think of the vector equation for R as 3 separate equations for x, y and z coordinates of the general point on the line. Here x is given by 2 plus lambda, y is -1 -3 lambda, and z is -5 plus 2 lambda. If we rearrange these equations, we find that lambda is x minus 2, 3 lambda is minus y minus 1, and 2 lambda is z plus 5, so that by equating each expression for lambda, we can obtain the Cartesian form of this line, equivalent to y equals mx plus c. We obtain the Cartesian form of this line in the form lambda equals x minus 2 equals minus y minus 1 divided by 3 is equal to z plus 5 divided by 2. Of course, we could have chosen the point B as our starting point. We can also choose any vector parallel to the line. For example, we could have chosen this vector, minus 2, 6, minus 4. This now gives us the equation of the line as r is 3 minus 4, 3 plus mu, a new parameter, times the vector 2 minus 6, 4. Although this formula looks very different from our earlier equation, it gives us exactly the same straight line. What we've done is to change the parameter value associated with each point. For example, the point B is now given by mu equals 0, whereas previously it corresponded to lambda equals 1. In fact, all we've done is to simply replace lambda with 2 times mu plus 1 in our original formula. So now r is 2 minus 1 minus 5 plus lambda 1 minus 3, 2. And if we substitute lambda as 2 mu plus 1 and then rearrange for mu, we recover the formula 3 minus 4, 3 plus mu times 2 minus 6, 4. A common question asked in A-level examinations is to determine whether a particular point lies on a straight line. In this case, we wish to determine whether the point C, which has position vector 0, 5, minus 9, lies on our straight line. If it does, then there must be a value of the parameter lambda that corresponds to this point. Therefore, if we can identify this value of lambda, then we have proved that the point lies on this line. Let us consider each coordinate separately. At the point C, the x-coordinate is 0, so that 0 equals 2 plus lambda, from which we can conclude that lambda must be equal to minus 2. We now need to check that this is consistent with the equations for y and z coordinates. For a point on the line, y is equal to minus 1 minus 3 lambda, and so at lambda equals minus 2, this gives us minus 1 plus 6, which is equal to 5 as required. And z is equal to minus 5 plus 2 lambda, which is equal to minus 5 minus 4, and equals minus 9. So all three equations are satisfied, and therefore this point does indeed lie on the line and corresponds to lambda equal to minus 2. Now let's repeat this exercise, but for the point D, which is equal to 20 minus 7, 19. Examining the x component, we find that 20 is equal to 2 plus lambda, which gives us that lambda is equal to 18. Now let us check the value of y. Minus 1 minus 3 lambda is equal to minus 55, which is clearly not equal to minus 7. Therefore, there's no value of lambda that satisfies both the x and y equations. In this case, we don't need to check z, as we know that it won't work. And so D does not lie on this line. So let us answer a second question. Which point on the line is closest to D? To begin, let us consider a general point P on the line, which has position vector given by r equals 2 minus 5 plus lambda 1 minus 3, 2. And consider the vector dp from D to this general point. What we need is a criteria for when the length of dp takes its smallest value. If you think carefully about this diagram, you'll see that this occurs when dp is perpendicular to the direction vector of the line. Now recall that if two vectors are perpendicular, then their dot or scalar product is equal to 0. This means that in order to find the closest point on the line D, we need to find the value of lambda for which the dot product of dp with the vector 1 minus 3, 2 is equal to 0. Now, the vector dp is equal to OP minus OD, which is the vector r, the general position on our line, minus 20 minus 7, 19. Now, taking the dot product of this with one 3 minus 2 gives lambda minus 18 minus 3 times 6 minus 3 lambda plus 2 times 2 lambda minus 12, which simplifies to 14 times lambda minus 84 equals 0. Hence the value of lambda corresponding to the point P, for which dP is perpendicular to the line, is equal to 6. Substituting this value into the equation for the line gives the point P, which is closest to D, as 8 minus 19, 7. In this case, the vector dP is given by minus 12, minus 12, minus 12, which is indeed perpendicular to 1 minus 3, 2. To find the minimum distance, we need to calculate the length of the vector dP. Since dP is minus 12 times the vector 1, 1, 1, it's easy to see that this is simply 12 times the length of the vector 1, 1, 1, i.e. it's 12 times root 3. The key to solving this last problem is to use the parameter lambda to encode the position vectors of all the points on the line, and then to determine the particular point of interest by finding the one value of lambda that satisfied the condition required of the particular point we want to find. In summary, the vector of the equation of a line requires two vectors: the position vector of one point on the line and a second vector defining the direction of the line, which can be found from the position vector of a second point. The result is a parametric equation giving the coordinates of all possible points on the line in terms of a parameter that varies from minus infinity to plus infinity. Since any point on the line must be of this form, we can show that a point lies on the line by finding the particular value of lambda that corresponds to this point. Furthermore, by allowing lambda to be a variable, we can find general expressions for other vectors, such as the vector from a point to the line, which we can then manipulate.